first of all, I prefer to interrupt me if something is not clear, because I don't know exactly what your background is, and we don't have that much common background maybe. If I talk a lot or very if I talk about the subject that is not clear for you, don't hesitate to interrupt and ask. First, I will introduce myself. My name is Meysam Shamsi. I'm enseignant-chercheur at the department, a computer science department, and I will do my service in INSIM, École Ingénieur. My research interests are around two main axes. I'm interested in human-machine interaction, which can contain human-assisted learning, how we can use human in the loop of the machine learning. It can be applied from the diarization, speaker verification or anonymization to speech synthesis, which was my PhD topic in the University of Laboratoire. I have worked on speech synthesis, text-to-speech systems. I'm also interested in perceptual speech quality evaluation, particularly in speech synthesis type. Also, I'm interested to work on the explainability and analysis of the speech characteristic. Interpretability, explainability, and representation learning can be a good point of view for a new machine learning era. So it helps us to understand what's going on in the black box of the machine learning and deep learning in new technology and new research. I'm also interested and started to work on the emotion, prosody, style, and notation of the speech, analysis of the emotion of the human speech. But today I will present you my postdoc work, which has been done in the Lyon and the LST team under the supervision of Monsieur Larchet, Anthony Larchet. And it's under the title of Benefit of Human-Assisted Learning for Speaker Diarization. So first of all, what is the speaker diarization? If we want to put it in the small word, we can say we want to answer the question of who speaks when. So if we have a speech signal, first we need to answer when somebody is speaking. We need to segment our speech signal in the axis of the time. And after that, we are interested to know who is speaking in that specific time. I should mention that we don't want to answer the identity of the speaker. We just need to find out where same speaker are speaking. So we call it this process as we treated this process as a clustering process. So it means that we just want to know which segments are in the same cluster or belong to the same speaker. And we don't talk about the identity of the speaker. So if I want to give you an idea how the state of the art of the speaker diarization work today, the simplest way or very classical way is using hierarchical agglomerative clustering for speaker diarization after a segmentation step. So for a given IDU file, we run a segmentation process to find out where we have a speech and where we have music, silent, or noise. This process can be done by using another system which is out of the scope of this presentation, which called DAD, voice activity detection, is another system that runs and find where we have a speech and where we have noise, music, or silence. So after this step, which is the main concern of this presentation, we have a segmentation. We have a segment of a speech. We want to know which segment has the most similarity to others to find a cluster of the segment which can be interpreted as or which can be presented by a speaker. So the idea is we can calculate, if we are succeed to calculate the distance between each segment, we can create a tree, hierarchical agglomerative clustering, and a tree which represents the distance. So for example, this segment has this amount of distance from these two segments, and this segment has this amount of distance from this segment. So the distance can be from the 0 until infinity, theoretical. But if we find this kind of distance, we can create this tree. So in speaker diarization, the only thing that we need after creating this tree is finding a threshold, and based on this threshold, say that okay, after this distance or this level of the similarity, we consider this segment as a one speaker. But how we can find such a distance? We can compare, classically, we can compare different characteristics of the segment, but thanks to the deep learning and new architecture in the neural network, we have a method that's called X vector for extracting a characteristic from a segment, a speech segment, a signal. So this characteristic can be compared to another, and based on the Euclidean distance, we can interpret the distance between two segments. But the X vector, how we calculate the X vector? If we have a given signal correspond to a specific speaker, we can train a neural network such as this one for a speaker recognition task. The speaker recognition means we have a signal, we train the model to find out what is the class of this segment, class of this given idea. So the final output would be one out of the class of a speaker. But if we, after training of this neural network, we remove the last layer, which do the classification task, we can arrive to another information before this layer, which can be interpreted as all the information which needed for classification task, for finding out what is the characteristic of this speaker speech of this speaker. So it's the idea of the X vector. We can train a network like that and find and extract a vector per segment. But what is the human assisted learning inside the diarization task? Diarization task, thanks to the new research and study, arrive to a certain level of the performance, but still it cannot be implemented in the real life and needs some observation or supervision. So in this presentation or in this work, I will present you that how much we can gain from having a human in the loop of the speaker diarization. So we can imagine we have different signal and we have a diarization system. This diarization system can generate a segmentation and clustering to represent the corresponding speaker to each part of the signal. But we can improve the performance of this diarization system by having a human in the loop of the learning. We ask the diarization system can generate a question based on its confidence and certainty about the result, generate a question, human can answer this question as a ground truth information and do a feedback to the system. This feedback can be done by an adaptation module, which adapts the diarization system, or a correction module, which directly correct the diarization system, diarization result. So in this study, as a first step, we only concentrate on the correction module. So we generate a question, human will answer, and we correct the output. And based on that, we want to know how much we can gain in the term of the performance of the diarization. So the idea of having human in the loop need first need is to generate a question in this step. The diarization system need to generate a question. So how we do that? First of all, this generated question is some representation of the certainty of the model or the confidence of the model. If model is not confident with his prediction, he should generate a question and get a confirmation or correction from human. To do so, we propose an algorithm that provides this kind of information, the certainty of the model. As I said, once again, we can run a hierarchical agglomerative clustering to cluster our segment, which is resulted based on the segmentation process. And after that, we extract X vector from this segmented group and generate a vector per segment, per group of segments. We do this part because if we start from the extracting X vector per each segment in the lowest level, we don't have enough information for X vector extractor. So we run a grouping to group or merge very small segment that is the result of the segmentation process. And after that, we run a X vector extractor and have a one vector of the characteristic per group of segments. Afterward, we run another clustering, hierarchical agglomerative clustering, and based on a threshold, we can find a group of speaker, a group of segment corresponding to a speaker. I should mention that this threshold that I'm talking about can be fine-tuned based on a part or part of the data set that we have the ground truth of the information. So the human-assisted learning comes in this step. After having this threshold and doing this clustering, the human-assisted learning can modify the threshold and based on the confidence or the initial distance that is calculated by model, it can modify the result to improve the performance. So we are only talking about the changing the definition of the threshold in a hierarchical agglomerative clustering to improve the performance of the diarization system. So it was the idea of how we can use the human in the loop of the diarization, but what our approach is exactly like that. So I give you more detail about the approach or the experimental design that we had. So for a given baseline diarization system, we have a system of diarization system. It clusters some segment of the signal as one speaker. So we can see these red segments belong to this cluster, the blue one belong to that one, and etc. So for a given diarization result, we need first step, we need to generate a question and ask human to correct and improve the result. So to do so, first step, we split our segment, our clusters into the another bottom line group of segments to have the chance to split one speaker to several speakers. So we can run for each group of segments that exists in each cluster another graph, another dendrogram, which represent the distance of this segment to each other. And based on that one, we create another threshold as our baseline and consider this threshold as our bottom line clustering. So our model, our interaction with human will not change the merging of these two clusters, but it can merge them in these points. So in another level, we can run another hierarchical agglomerative clustering on top of our baseline system to merge the clusters. And we come to this schema. So we freeze this step. We are investigating, we are questioning about the correctness of this part. So if we are investigating in one, it means that we are all segment that belong to the cluster 1 and cluster 2, which in our baseline are separated, should be grouped or not. Or they belong to the same speaker or not. So if I want to put it in one sentence, we are just looking into the number of the speakers in our diarization system, and we want to correct that one. So if I split this cluster in two clusters, I increase the number of speakers by creating a new group of cluster. If I merge these two speakers, these two clusters, I reduce the number of speakers. So, as I said, the threshold has been defined by a training set, a data set, as a ground truth. And the model generates this schema, this dendrogram, based on this threshold. The distance of each node from the threshold can be interpreted as a certainty or confidence of the model to its result. For example, this point, this node, is close to the threshold, which means model, if we change a little bit about, the information inside the database, the threshold can go down, and this node can be split in two subclusters. So the closest our node to the threshold is, more suspicious is. And the model based on that one can generate a question from human. So here the model generate a question about first one, after about second, third, and fourth, 5, and 6 based on the distance from the threshold. So in order to facilitate the interaction of the human and machine, human and the system, we simply we design the system to generate one simple question. Are these two segments belong to the same speaker or not? It selects two segments from each cluster, and after that provided to the human, and human listen to that and answer by yes or no. To generate such a question, we need two things. First, which segment from chosen cluster and which cluster we need to choose. So to answer the first question, for a cluster, if we want to investigate this node, which means that we want to know these two segments and these three segments are belong to the same speaker or not, we need to choose one segment out of these two and one out of these three. We tested several methods to find the best one. We can randomly select one. We can select the largest one, longest one. We can choose the cluster center. Each of these parts can be considered as a one cluster, subcluster. We can choose the most just two segments with maximum distance or minimum distance. We did a small experiment and we find out if we select the longest segment, we arrive at the best result. So for the answer to the first question, for the second one, how we choose the cluster, as I said, we follow the order of the distance or difference from the threshold. So we sort the absolute distance or the difference of the cluster from the threshold, which means 1 to 6 here. And after that, we investigate in order from 1 to 6 the grouping or the separation of the subcluster. In order to control the cost of this human interaction, we set another stopping criteria here. We set a stopping criteria. We can investigate all these 6 ones, but it costs a lot if the system has a confidence. So we set another criteria to stop the process of question generation, which called confirmation to a stop. So when the system gets a confirmation here, which means these two clusters should be separated, confirmed by human, we will not investigate this node or this node. We stop. Or when we get a confirmation from this step, which means that these two subclusters should be merged as it is in this level, we will not investigate the node below that one. So if we ask a separation question, which means a question that is below the threshold, we have two situations, a confirmation or correction. If we have the system generate a clustering question, which means a node upper than threshold, we have still two confirmation or correction answers. The confirmation to a stop, we define as a number of times that question need to get a confirmation to stop the process of question generation. So if system ask a question based on his confidence, and he get the answer of confirmation. The human confirm his knowledge. He will not continue in that direction by asking another question with more confidence. So in order to evaluate the diarization system, we have a metric called diarization error rate. I just give you an idea what is the important in diarization. The diarization error rate is the time that system has an error divided by the total time. The time that considered as an error can be a missed time, a part of the signal that is belong to a speaker, but that this doesn't take into account as a speech. So in the hypothesis, the generated sequence of the system, this part didn't take into account as a speech or any speaker. It can be another part of error. System consider one part of the signal as a speaker when we don't have such a thing in the reference. Or we can have another error which called confusion. System consider one part of the signal as a speech, but with wrong cluster or wrong speaker. I should mention that our human assisted learning only investigating this kind of error, because the missed time and the false time coming directly from the segmentation. So as a first step, we only want to improve the performance of the system by minimizing the confusion error. So another metric that needs to be taken into account in our work is the performance of human interaction. So we are interested to ask a question which will get a correction, and the correction improve the performance of the system. So we define a question performance metric, which is simply the division of the number of times that we have a correction divided by number of the question that system generates. And we want to maximize this one. Because asking a question or having a human in the loop has a cost. And also we take into account this cost in our diarization error rates metric, and we called it penalized diarization. So when we have an interaction, we generate a question and have an interaction with human, we penalize the diarization error or add new error to the system as a cost to see asking such a question worth the benefit of improvement or not. So we can have several situations. I will talk a little bit about the system. So if we define a interaction cost or interaction step, we can have an initial state of of two systems, system 1 and system 2. By having an interaction, we hope that the error will decrease by correcting the output. But the correction at the meanwhile can be same, and two systems can have the same performance from the first to end. So in that case, we can say system 2 outperforms system 1. But we can have another type of situation like this one. System 1 and 2 has almost same initial state, initial performance, but when they have an interaction with the human, system 2 shows a more stability in the performance improvement. It's another aspect that should be taken into account in our study. Or we can have another situation. System 1 is better than system 2 at the beginning. System 2 is better than system 1 because here we have an error. But by having human in the loop, the system 2 profit more from the human. System 1 profit more from the human and interaction and reduce its error more. So if I want to give you a real example in our case, here is a comparison between two stopping criteria, which means when we stop generating the question for two IDEO file, based on the number of questions that we will ask. So you can see if we ask only 5 questions, we can improve the diarization error to this point. But if we have, we will ask more questions, we can improve more. But the point is when we should stop, and it's the big question of this study, when we should stop, because sometimes by asking a question and getting a correction, we can even have an increase of the error. Because we just modify one part of the endogram, and it can cause an error in whole of the in the general view. So to run an experiment, we had a data set called ALICE. It's contained around 1,000 French TV show from 8 radio station and TV channel. So it's around 328 hours of the speech signal. Not a speech signal only, it's a signal, and 96% of this time we had a speech. The rest would be silent music or noise. So in order to run an experiment, we evaluated our approach of having human in the loop by 2 baseline systems, 2 diarization systems, and 2 types of initial segmentation. First, I will talk about the system that we had. All that I explained about baseline system for the diarization with the dendrogram and tree called evaluate system, which is based on a hierarchical agglomerative method for the clustering and use the X vector. But there is another system, which is another state-of-the-art system in the diarization task called VBX HMM, which use the hidden Markov model for clustering, and it can change inside the clustering stage, can change the segmentation as well. So this one is based on HAC. This one is not based on hierarchical agglomerative clustering, and we compare these two because our confidence is based on hierarchical agglomerative clustering. And this model doesn't take into account this information inside his training or his prediction of the first step. So about the segmentation, we also compared 2 types of the segmentation. First, we used voice activity detection, LSTM-based voice activity detection that trained on our dataset. Also, we used a reference segmentation, the ground truth segmentation, to see how much of our final error comes from the segmentation that we didn't take into account in our interaction. So if we want to compare the diarization error of this system as a baseline, we can see that on our data set, the VBX has a better performance than our system in both cases, when we use the reference, when we use the VAD, voice activity detection. So we have one system which perform better, but it's not adapted to our confidence method, definition of the confidence. When we use the, and I should mention that the confirmation to a stop, the number of times that we get confirmed and after that a stop to generate new question, we set to the 1, 2, 3, 2, 4, and infinity. For infinity means we don't take into account the confirmation to a stop and we investigate all the possible questions that can be generated by our tree. So you can see that if we increase the confirmation to a stop, the gain that we have is increased. So we reduce the error in both cases. And finally, we can have a 10% improvement for evaluated X vector and 5% for VBX HMM. This difference between evaluated X vector and VBX HMM can be due to the high quality of initial diarization result, or can be due to the method of the definition of the confidence or certainty of the method that is more adapted to the system. Okay, to analyze the interaction, we can see that the number of questions, when the confirmation to a stop is increased, the number of questions also increase. So it's exactly what we expected, but when you compare the VBX and the evaluated, we can see that at the beginning, for confirm to a stop equal to 1, we have more question for evaluated X vector, but less question for the another. And also, the more interesting point is comparing these two graphs. By increasing the confirmation to a stop, we increase the number of questions, but we decrease the quality of the question. Quality of the question, number of correction to question in the ratio. So it means that we can gain more improvement, but with more cost when we generate more questions. So if we want to compare the final result to a baseline, to the baseline performance, here we calculated the penalized DER as well. And as I said, the penalized DER is number of the time that we generate a question multiplied by a time as a cost. This time of the cost can be the time that we need from human to answer our question. Listen to these two segments and make a decision, give us a feedback. So if the penalized time, this interaction is equal to 1, we have one situation, the yellow one, the number of the added error would be very small, but when the penalized time is higher, the added error or added cost to the DER would be higher. And you can see that sometimes by having a higher penalized time, the final penalized DER is higher than baseline system. So the interpretation can be after a certain point is not worth it to ask question, or after certain cost of the having interaction is not worth to ask a question. So I added another. Okay, so I just make it short here. We added another step on top of the question generation to estimate the quality of the generated question before asking. So and we find out that if we, and this the quality estimation of the questions are based on the clustering evaluation, such as Twinsky-Harvards, and before asking a question about splitting one cluster into two or merging two clusters to one, we evaluate the performance of the clustering, and if the performance would be increased, we generate a question. And to do when we do that, we can see that the final DER, by having this conditional questioning, would be almost same for all, but the number of questions will be degraded significantly. So we have less question in all different situations compared to the original approach, but the final DER will be same. The last slide is about how we can decide, or the big question that remained to answer, how we can decide when to stop generation of the question. In this figure, I plotted the penalized DER based on the interaction cost. So if I consider each interaction cost as a 2 seconds of the error, how much I will have the final DER, penalized DER. And when we have 8 seconds of the same as 8 seconds of the error, how much I have there. And by comparing the final error with the baseline DER, we can see that where is worse to have this interaction, and when we don't have, it doesn't worse to have this interaction and this question as question generation. So you can see after this certain point, for example, the system without question generation will increase the final penalized DER from the baseline. So if our method, the importance of having interaction or the cost of having interaction is more than 3, most of the time the system cannot improve himself based on the cost that he has. That's it. Thank you.